Okay. So I'm just going to do a quick introduction for everyone here.
All right.
So let's pull it up. So we're recording. In Parsa, we're recording. Okay. So welcome everyone to the 2024 Turing Award winner speaker series here at the Georgia Institute of Technology, College of Computing. This event is sponsored by AI2 Incubator. During the course of the semester, we have 5 Turing Award winners, 1 Nobel laureate in physics, many other famous computer scientists that will be speaking and giving presentations to 2,000 plus RCP students and faculty from top computer science universities in the world. Thank you very much to our esteemed speaker series advisors, Dr. Spiegel and Dr. Bjarne Sestrat, for helping to make this initiative a reality. So grateful for your advice and guidance as we planned this tremendous speaker series. Thank you as well to our LinkedIn influencer and sponsor, H. Sarvizian, for assistance in helping market the series to her 485,000 plus LinkedIn followers. We simply could not have achieved our attendance numbers without you. I'm extremely excited to announce our speaker, the insanely accomplished computer scientist, Dr. Jack Dongarra. Dr. Dongarra is a computer science mathematician. He's the American University Distinguished Professor of Computer Science and Electrical Engineering Computer Science in the department at the University of Tennessee. Holds the position of a Distinguished Research Staff Member at Oak Ridge National Laboratory. And he worked at Argonne National Laboratory until '89, becoming a senior scientist. He specializes in numerical algorithms for linear algebra, parallel computing, the use of advanced computer architectures, program methodologies, and tools for parallel computers. So research includes the development, testing, and documentation of high-quality mathematical software. He has contributed to the design and implementation of the following open source software packages and systems: EISPAC, LinPack, linear algebra subprograms, linear algebra package, ScalaPack, parallel virtual machine, message passing interface, NetSolve, top 500, automatically tuned linear algebra software, high performance conjugate gradient, performance application programming interface. These libraries excel in the accuracy of the underlying numerical algorithms and the reliability and performance of the software. They benefit a very wide range of users through incorporation into software, including MATLAB, Maple, Wolfram, Mathematica, GNU, Octave, the R programming language, SciPy, and others. With Eric Gross, is that pronounced Gross? You pioneered the distribution via email and web of numeric open source code collected in NetLib. He's published approximately 300 articles, papers, reports, and technical memoranda, co-author of several books. He served as a Turing Fellow since 2007. He was awarded the IEEE Sid Fernbach Award for his contributions to an application of high-performance computers using innovative approaches. Without further ado, I give you guys Dr. Jack Dongarra. Everyone, let's get a massive applause, virtual applause here in the audience. Let's go, guys.
Right. Okay. So, well, thanks very much for that kind introduction. I don't know if I have much time left to talk, given okay, so you know my background a little bit. I'm at the University of Tennessee. I work at Oak Ridge National Lab, and then I have an appointment at the University of Manchester in the UK. I'm going to talk about some issues related to software and high-performance computing. But let's start by looking at the situation that we have today. We really have a changing world. Computers pervade almost every aspect of society. They impact e-commerce, business, research and development, and companies like Apple, Samsung, Google, and Huawei really dominate the smartphones that we have. And if you take a look at the chip, I'm giving this talk on an Apple Mac. It's got a M2 processor on it, and just incredible specifications for this processor. With just an incredible array of of cores associated with it, 8 cores for the CPU and 10 cores for the GPU. Just an amazing device, which I use, again, mainly I use this device for reading my email and giving talks. So it's just a stunning piece of engineering. We have a number of companies here that really have made tremendous strides here. Google, Microsoft, Amazon, and Apple they really dominate the stock market. Each of them having over $1 trillion capitalization. So their net worth is over $1 trillion. And some of the Chinese companies are not far behind. If we take a look at the more traditional computing companies like, let's say, Lenovo and HPE and IBM and others, Intel, they have in aggregate only $1.4 trillion. Their net worth. And if we take a look at the AI community and what they've done through NVIDIA, they've reached a point where they've eclipsed Facebook and almost approaching Amazon in terms of and Google in terms of their net worth. So just an incredible situation in terms of computing. So we in the scientific area use NVIDIA to drive some of our computations. AI certainly uses that as a mechanism, and that's really the reason why NVIDIA is doing so well today. And these cloud vendors, when you take a look at what they're doing, they're designing their own processors. So companies like Alibaba, Amazon, Google, and Microsoft, they have designed processors to help them service the cloud community. So they're not selling these processors, they're using them. So you can't buy one of these processors. You can buy the service that's offered by these companies that make use of these processors. And even car companies are getting into it. So Tesla has their own processor, which they've designed to help with some of their AI needs and help service their community. So just an incredible situation we have today. And what happens in the future is a little bit uncertain. I work in the scientific area, so high performance computing is important. High performance computer really drives science today through simulation. So science is really done on high performance computers today in terms of driving simulation. We have this list called the top 500. So this is a list of the 500 fastest computers. We started this list back in 1993. So it's a little bit over 30 years old. And when we started this list, there were just a few machines, 65 systems of the 500 machines, 65 used Intel processors. And the remaining systems use more specialized architectures, mainly in the form of vector processors. So we had companies like IBM and Cray and SGI and NEC and Fujitsu and Hitachi, which really dominated the scientific computing arena in terms of supplying specialized machines that had very high performance, that had specialized processors that did vector-based computing. And that story changed. And it changed around 2004. And what happened in 2004, we had this incredible situation with microprocessors becoming much, much faster. So what we've seen since that point is Intel and AMD, both using the x86 architecture, the instruction set, have really dominated the chips that are used in the top 500. So today we see that they have a majority, 97% of the systems, 97% of the 500 computers use x86 instruction set that come to us through Intel and AMD. And many of these machines also use GPUs to boost the performance, to get it up to the point where high performance computing can be obtained. And many of those companies that really specialized in scientific computing have gone out of business. So companies like Cray has stopped building vector computers. IBM have stopped building vector computers. Cray have really been folded and been incorporated into other companies at this point, SGI and Thinking Machines as well. And there are a few Chinese companies that still are in business making high performance systems, but the whole field has really changed as a result of the microprocessors taking over. And what we've seen is that if we take a look at the 500 computers again and look at the frequency of the chips that are used in those 500 computers, we see that the frequency has increased over time. And that's really been the result of Dongarra scaling. So Dongarra scaling says we can shrink the dimension of the chip, so we get more gates on the chip. And if we do that, we can really control the power that's required for that chip. So we get smaller transistors on the chip that use less power and cost less. And the result of that is we have really a high performance scenario for building chips, which can really boost performance. So in the old days, when I got a new computer and had a higher frequency, I didn't have to do anything. All I needed to do is put my application on the computer and it ran faster as a result of Dongarra scaling. So that in some sense is the secret sauce that's associated with Moore's law. And unfortunately, Dongarra scaling came to an end roughly in 2006. And the result of that has been we are no longer seeing the frequency of the chips increasing. So that's been stabilized at a point. And Moore's law is still in effect. So we're seeing more gates on the chip. And that has resulted in more cores being put on the chip. So the frequency is stuck at a certain point. And Moore's law is driving the number of transistors that we have on chips. And those transistors are turned into more cores that we can use to enhance the performance. So something that resulted in a hardware situation, more cores on the chip, resulted in a software situation that we have to face in terms of designing our software so that they use those multiple cores. So we no longer have the luxury of riding that Dongarra scaling curve where we just got this benefit of having a higher frequency resulting in our programs running faster. So smaller devices with thinner dielectrics and shorter channels produced more leakage, and that leakage caused chips to heat up. And that's why Dongarra scaling ended at roughly 2004. The situation is something like this. The power required for chips today is proportional to the voltage squared times the frequency. And the voltage and the frequency are related as well. So the power goes something like the frequency cubed. So think about the frequency of our chips, and now think about making the chips twice as fast. And if we did that, the power requirements would go up by a factor of 8. So right now our chips are chips that are used in desk side machines are roughly at 100 watts. And if I go up to 800 watts, I have a real issue in terms of cooling those chips so that they can function properly. So Dongarra scaling ending caused a number of problems, and that has resulted in multi-core, has resulted in the forcing the use of parallel processing to really get more performance. Today in high performance computing, we use accelerators, and those accelerators help boost the performance. And this is looking at the top 500 machines again, and we're looking at the number of machines that use accelerators. So back in 2006, there were no machines that had accelerators. They didn't exist. And we see this rapid increase over the years in terms of accelerators that are used on the top 500 systems. So today, NVIDIA dominates this market, producing many of the accelerators that are used on the supercomputers that we have today. So the 500 machines, 160 of them use NVIDIA accelerators, and around maybe another 30 use accelerators that are produced by other companies. And other companies do produce those accelerators. Intel, AMD notably produce accelerators which are being used in high performance systems. Of the 500 computers that we have today, 85% are connected by Ethernet and InfiniBand. So we have 426 of the machines that are that are connecting their processors together using that form to do the interconnect. So we have commodity processors, commodity accelerators, and commodity interconnects that are being used to drive high performance computing. And the main reason for that is to keep the cost of those computers down. And Linux, of course, is everywhere on those machines. So the Department of Energy is a heavy investor in terms of high performance computing. They use it, of course, to do simulation. So simulation drives science. The Department of Energy had a program that was called the Exascale Computing Project. And that was a 7-year project that cost $4 billion. So the question is, what do you get for $4 billion? Well, they got 3 computers. One of those computers is at Oak Ridge National Lab called Frontier, and that's a system that's based on AMD parts. Another machine called Aurora is being put in place at Argonne National Laboratory outside of Chicago, and that's an Intel-based machine. And the third system is called El Capitan, and that's the one that's going to go into Lawrence Livermore National Lab out in California. Each of those machines cost $600 million. There was $400 million given to the vendors to help them think about high performance computing and put that into the hardware to really help go beyond those commodity processors that we have. In addition to that, so basically half of the money was spent on hardware, and that's just the hardware. And then the rest of the money, the rest of the other $2 billion was spent on applications. And the Department of Energy has singled out, well, not singled out, but they have specified 21 applications that was going to come under this program. And those applications are listed here. They're all related to energy in some sense, like wind energy, carbon capture, materials, quantum chemistry, photon science, nuclear reactors, and various things in terms of enhancing things like combustion engines. And the other half of the money of that $2 billion went into software. So about $1 billion went into software to help those applications run efficiently on those high performance computers. These are highly parallel systems which are being used, and software needs to be redesigned as well as the applications to fit on these systems. So that project was a 7-year project, and it just ended. It ended in December, and there were 800 people that were working on that project. And those 800 people work mainly at the Department of Energy laboratories, and those people are scrambling right now to put together funding so they can stay in business. So there was no follow-on project at this scale to carry things forward. They wish they had a project. I think the project that was wished for was AI for science, but it didn't materialize in time. So many of these 800 people are now scrambling, and many of those people will end up going to the hyperscaler companies to find positions. And it's a loss really for the Department of Energy. So if we take a look at the HPC environment today for scientific computing, we see one that's highly parallel. It's based on distributed memory. It uses MPI as the way to pass messages between the processors, and it uses OpenMP to help with the programming model in a shared memory context within a node of a system. One of these machines, called Frontier at Oak Ridge National Lab, has a peak performance of 2 exaflops. And I'll talk about an exaflop in a moment. This machine has 8.8 million cores in it. There are 9,408 nodes in the machine, and this system consumes 30 megawatts of power. So 1 megawatt is, to get a grip of that, if I use a megawatt at my home over the course of a year, I'm going to get a bill from the electric company for $1 million. So a megawatt year is roughly $1 million. So this machine at Oak Ridge, in order just to turn it on, is going to cost about $30 million a year. Of course, the cost of the machine itself is about $60 million. So we have to take that into context as well. The environment that we have is heterogeneous for doing computing. It's based on commodity processors and commodity accelerators. And we have to design programs that basically juggle those two components so that we can effectively drive performance. Communication is something that is very expensive on these computers. In the old days, communication was not so expensive, and it was floating point arithmetic that was the most expensive part of doing operations on these computers. But today, our computers are over provisioned in some sense for floating point, and communication becomes the most critical resource that we have. So I had this notion of when I look at applications, and if I have two algorithms to choose that roughly do the same thing, and I look at the operation count for those algorithms, and I would choose the one that has the fewer operations because it would run faster. That was true in the old days, but that's not true today necessarily. Today, we also have to look at the communication pattern and understand how much communication those algorithms are performing. And it may be the one that does fewer communications is the one that would be preferable or be easier to optimize. And on these high performance machines, the traditional way of doing scientific computing was using 64-bit floating point arithmetic. 32-bit was always there, but today we also have options for doing 16-bit and 8-bit floating point arithmetic. The 8-bit and 16-bit arithmetic is there really to drive AI applications. So the hardware manufacturers realize that AI applications, machine learning, does not need such high precision. So they can get much faster operations by reducing the operand size, and they've done that on these machines. Okay, the fastest computers we have today go at an exaflop. Well, first let's talk about a floating point operation. What is that? So whenever I'm talking about floating point operations in this context, it'll be an add or a multiply of a 64-bit numbers. So taking 64-bit numbers, adding them or multiplying together, each of those would cost one floating point operation. So we have an exaflop machine. So that's a billion floating point operations per second. I sometimes have a hard time getting my hands around that number, a billion, 10 to the 18 operations per second. So think of it like this. If each person on Earth completed one calculation per second, it would take about 4 years to do what that exascale computer can do in just 1 second. So 4 years of each person on Earth doing one calculation is equivalent to an exascale worth of computation. So it really is an enormous way of doing that. Here's another way of looking at it. If we give everybody a laptop that sits in the Bobby Dobbs Stadium there at Georgia Tech, and those laptops can perform around 5 times 10 to the 11 operations per second. That's the laptop I'm using to give this talk as an example. This is an Apple Mac system. And we think about connecting all those machines together in the stadium. That would give us about 27 petaflops. So the question now is, so we have 55,000 seats. Each person that's sitting there has a laptop, and some magical way we have of connecting them together that results in a computer that has a peak performance of 27 petaflops. So the question is, how many stadiums do we need to get to an exaflop? And the answer is 36 stadiums. So just an incredible amount of computing that we have at the exascale level, putting that into perspective. I became an accidental benchmarker back in 1979. I was involved in a project called LinPack. LinPack is a software package for solving systems of linear equations, and I was involved in the design of that package. There were 4 authors to that, and they're listed here from the right. There's Jim Bunch, who's holding the cup. Next to him is Pete Stewart from Maryland. Next to him is Cleve Moeller from the University of New Mexico. And that's a 1979 version of me with a little bit more hair and my car, which has a LinPack license plate from New Mexico, where I got my PhD. So in the appendix for that user's guide for LinPack, I put together a little table. And that was a table that was put together for solving a simple system of equations, a matrix of size 100. And it was put together and it I've recorded the time it took to solve that system of equations using our software. And that turned into a table where the time was converted to megaflops. That's my handwritten scratching there. That converts it to a megaflop rate. So the fastest computer back in 1979 was a machine at the National Center for Atmospheric Research. It was a Cray 1 computer, and it ran at 14 megaflops. And you could see the rest of the machines there in terms of the performance. So that table became the basis ultimately for the top 500 list. I had a colleague in Germany, Hans Moyer and Eric Strohmeyer. They had a list of the fastest computers that were ranked by peak performance, and Hans suggested that we put our two lists together and call it the top 500. So that's where the top 500 list originated. So it's basically solving a dense matrix problem, AX equal B. We're looking at solving it using the fastest method we can. That is using Gaussian elimination with partial pivoting, but doing the fastest implementation of that method. And that's been done since 1993. That list of the 500 fastest computers comes out twice a year, and it comes out in November and in June. So the most recent list we have is from November of 2023. And this is a snapshot, if you will, of high performance computing over the last 30 years or so. So the red dots are listing the machine at position number 1. So the fastest computer today is this computer at 1.19 exaflops. The slowest computer on the list, the guy that's just at the bottom of the list, is at 2 petaflops worth of computing. And between that is the bracketing of the 500 fastest computers. You can see I put some trend lines in, and notice that the trend line has this sort of discontinuity here where something happened in roughly 2008. Part of that, I think, is due to Moore's law slowing down, the Nard scaling ending, and maybe the financial crisis that we encountered at that point, which slowed down the rate at which new machines were put into the list. You could see back in 1993, the fastest computer was around 60 gigaflops. That's an interesting data point. It was a machine at Los Alamos National Lab. It was used for nuclear weapons simulation. It was a machine called the Thinking Machine CM5. It had 1,000 processors on it. The laptop I'm using today to give this talk, I can run the benchmark, and when I do, I get 426 gigaflops on my laptop. So not too long ago, that would have been one of the fastest computers on the list. So just incredible changes taking place in a relatively short time for this. This is a list of the top 10 computers today. And so this is the top 10 of the 500. The top 10 really add up to 56% of the total performance of those 500 computers. So really the top 10 machines reflect the major part of the performance. Then the way to read this is the machine at position number 1 is a machine at a Department of Energy laboratory called Oak Ridge National Lab. It's a machine called Frontier. It's integrated by HPE. HPE doesn't make any chips. They just take chips and put them together in a box and then sell that box to anybody who's willing to pay for it. In this case, they're using AMD chips. They're using an AMD accelerator. They have a very high speed interconnect, and they have 8,699,000 cores in the machine that was used to run this benchmark. And the benchmark ran at 1.19 exaflops, and that's 71% of the theoretical peak performance. So the theoretical peak performance is a paper and pencil calculation. Look at the rate of execution of floating point operations, count up the number of processors that you have, and multiply all that together, and that gives you the theoretical peak. So they've left on the floor 29% of the performance, but they've achieved something which is pretty impressive in itself. The power consumption is 22.7 megawatts under load, and the efficiency is measured in terms of flops per watt. And here they're doing pretty good at 52.6 gigaflops per watt. So just taking a look down the list, I've highlighted the machines that use accelerators. That's the listing in red here. So most of the machines on the top 10 use accelerators to boost performance. The only exception is this machine in Japan called Fugaku. It's based on an ARM processor that they've extended to use vector instructions. There's a machine here that's from Microsoft's cloud that's on the list, a very high performance machine. There's another machine at NVIDIA, which is used for some of their AI work. And the rest of the machines are used in scientific laboratories around the world for doing high performance computing. The system that we have at Oak Ridge, the exaflop machine, has a peak performance of 2 exaflops. It consumes about 20 megawatts. Each node of the machine has one AMD 64-core chip, and then it has 4 AMD GPUs associated with it. And then they put together 9,408 nodes in the overall system connected together with a very high performance interconnect. But if we were to do 16-bit floating point arithmetic, we can actually get a much higher rate of execution, 11 exaflops. So you can see the difference between 64-bit and 16-bit arithmetic that's there. Again, the 16-bit arithmetic is really for machine performance. And looking at the performance, we realize that most of the performance is coming from the GPUs. 99% of the performance of these systems comes from the GPU. So that says you really need to be using those GPUs to get performance on these systems. So this is looking at the #1 machine again from the beginning of the top 500 list. I just want to point out that we reached a teraflop, 10 to the 12 operations back in 1997. And that was a machine at Sandia National Laboratory. And then 11 years later, we got 3 orders of magnitude enhancement in a machine at at Los Alamos National Laboratory, that we reached a petaflop, 10 to the 15 operations. And then another 14 years it took before we reached that exaflop level in the machine at Frontier. So it's taking longer to get higher performance in our systems. And that has a lot to do with Moore's law. It has a lot to do with the cost of these machines and things that are driving performance as we go forward. This is a graph here that shows the top 500 systems. So there are 500 dots here. This is the fastest computer. That's number 2 and 3 and 4 and 5. And you can see this long tail associated with the top 500. So the real fast machines are at the top of the list. If I was doing this again, I probably would shorten the list. We don't really need to see 500 machines. We could look at the top 50 machines, and that would give us a good sense of the machines that are being used for scientific computing. There's rumored to be 2 or 3 exascale machines in China. So these are machines that actually would be faster than the machine that we have at Oak Ridge called Frontier. But China has slowed down. In fact, they've actually stopped reporting machines to us. So we really don't have a good indication of the machines. Back in 2022, they had the most supercomputers that are on the top 500 list. China had 162 and the US had 125. And today on the November list, China stopped reporting machines, and a number of machines have fallen off the list from China. So today they have 104 and the US has 161 machines. So we don't really get an accurate picture. China is afraid, I think, that the US is going to take some action against China in terms of limiting technology if they were to really expose the number of machines that they have. But China has a number of manufacturers. Lenovo, Inspur, Sugun, NUDT, and Huawei are the ones that make high performance systems in China. This benchmark that we use for the top 500 list is something which started back in 1979. It has a lot of positive features. It's easy to understand and shows trends. However, a lot's changed since 1979. Arithmetic was expensive then, and today it's over-provisioned and really inexpensive on our systems. LINPACK performance is no longer strongly correlated to what real application performance is on these machines. The LINPACK benchmark is basically doing dense matrix multiplication, and that's not typical of what we see in high performance machines today. So designing a machine that has a good LINPACK number may not lead to a good design choice for a high performance computing system. If we take a look at high performance computing today that we're using to do this simulation, we see it's being used in climate, combustion, nuclear reactors, fusion, materials, and accelerators. And those problems, we usually think about modeling them using a three-dimensional partial differential equation. So that 3D partial differential equation leads to a system of linear equations again, but that linear equation is no longer dense. It's a sparse matrix computation. So that really is the core part of many of these computations. And if we take a look at the standard way of solving that, it might be through an algorithm like the conjugate gradients algorithm. So this is an iterative algorithm. It's designed to solve large, sparse systems of equations. And we have another benchmark which looks at solving this problem. So if we think about solving that three-dimensional partial differential equation, we do a discretization. And in this case, we're using a 27-point stencil. And that leads to a banded matrix of this form here. A lot of zeros where it does have these stripes where numbers are located that we need to do our iterations on it. So we're doing a sparse matrix vector product to carry out this algorithm. So this is the results of that benchmark. So this is another benchmark. It has a shuffling of the order. So this column I'm highlighting here is the performance that we saw for doing the LINPACK benchmark, doing a dense matrix computation. And this is the performance we see doing this sparse matrix computation. And the interesting thing to note, so there's a shuffling of the order, but the interesting thing to note is that the fraction of peak performance that we achieve. So the fastest computer that we have here is the machine in Japan for this benchmark. And the fraction of peak that they achieve is only 3% of peak performance. And if we take a look at the machine that's number one for doing the top 500 benchmark, for doing the LINPACK benchmark, it achieves only 0.8% of its theoretical peak performance. So that's an incredibly low amount of performance. So we should be cautioned by that. And if we think about a race car and the potential to do 200 miles an hour, and if we're achieving only 2 miles per hour, we'd be very disappointed with that race car. So that says that these machines maybe are being designed not taking into account the kind of application that we would be interested in running on these machines. And there's a notable machine down here at the bottom. Number 10 is a machine in Japan. It's made by NEC, and they actually achieve a very high rate, higher rate of 5.4% of the theoretical peak performance. And this machine is based on vector operations and has an easier chance than some of the GPU-based machines. So I'm going to conclude here and say that the HPC hardware is constantly changing. It goes from scalar to vector to distributed memory to accelerated computing. And today we're looking at using mixed precision. There's been 3 computer revolutions that we've seen in high performance computing. There's been deep learning that I didn't have time to talk about, and edge-based and AI-based computing. And the way I think of this is algorithms and software always follow the hardware. So the hardware comes first. We have a certain amount of money. We ask the vendors to go off and build a piece of hardware that can run at a certain level of performance. It's built and it gets thrown over the fence, and then we scramble to try to make use of that. So, and we can do after a number of years, we can usually do a better job of modeling or putting our applications on these machines, but it takes a long time to do that. So there's really a lot of room at the top that we're wasting in some sense, and we should do a better job of looking at how we solve that problem. There was an interesting paper written a few years ago by Charles Lyserson and his colleagues. It was entitled, "There's Plenty of Room at the Top of What Will Drive Computer Performance After Moore's Law." It was in Science magazine. I would encourage you to go off and look at it. This is a riff, of course, on Feynman's lecture back in 1959, where he talked about quantum computing, basically. and saying there's plenty of room at the bottom. So with that, I'll conclude, and I'm happy to answer any questions that you might have. Thanks for your attention. I'm sorry if I went over a little bit.
Thank you so much, Dr. Dongarra, for taking the time to give us that presentation. So it looks like we do have some questions in the audience here. So I'm going to kind of just go through here systematically. Okay. So it looks like Brad McCormick in the audience said, speaking of China, what is the significance of the RISC 5 architecture? There's been a lot of hype around the specification, including China building a 3072 core system. Do you expect the RISC 5 architecture to be disrupting technology? And where does RISC 5 fit into high performance computing?
Right. So RISC-V is the architecture which is open. So it's something which is easily picked up. There's no license associated with it. Intel and AMD are the only companies that can make the x86 architecture, and they hold the license for that. But companies, or not companies, but the RISC organization, the RISC-V group has published the instruction set, and anybody can go off and take that instruction set and build a computer. So, so that in fact is what many people are. The Europeans have a big effort underway to develop their RISC-V architecture. China's looking very seriously at developing machines based on RISC-V. They don't have to worry about doing the licensing. They don't have to be worried about the U.S. imposing restrictions on technology going to China. They can just do it themselves. So it's a reasonable thing for to engage in. Today, none of the machines on the top 500 use the RISC-V instruction set. Now that may change in the future. Just to put that in comparison, I think there's only a handful, like 5 machines that use the ARM architecture. So ARM, of course, is another model. It is licensed, so you can pay for the license and then go off and design a machine based on that architecture. But only a handful of machines. Software, of course, is one of the hardest things to develop. Software, there's a lot of software already existing for the x86 instruction set, and the result of that is it's harder for people to migrate their applications to new architectures which deviate from that. So that's an uphill battle that many will face when moving to RISC-V or ARM.
Nirupama Ravi at Nokia Bell Labs asks, do you envision quantum computing replacing HPC? And what are your thoughts about the impact of infinite computing on data required?
You know, clearly quantum computing will be something in the future. But the question is, how long will it take to get to that point? How long will it take, or maybe it's always going to be in the future, is another way to look at that. So today we have a lot of people who claim to have quantum computers. We have very few algorithms that can be put on these quantum computers. Very little. I don't even know what the software environment, the ecosystem is for these quantum computers. So there's been a lot of hype around quantum computing. It's something that shows that it needs a lot of research before it can exist. I'm waiting for them to have a gate level quantum computer that has error correction. That would be the point where I think it makes sense. We're far from that point, from that stage. And in fact, I would say I'm going to be a pessimist here and say that I don't think it's going to happen in my lifetime. So it's going to take a long time. It's an important area of research. I think people should engage in it. But the reality is that I'm not going to replace my laptop with a quantum computer anytime soon.
Interesting. And then one other attendee says, what impact will AI have on the future of high performance computer design?
So AI, machine learning, is having a tremendous impact on scientific computing today. Almost all applications that are being produced today are using AI and machine learning in some way. And that's going to increase in terms of how much they're used in those applications in the future. So it is an important concept. It's showing great promise. It's something which I think its time has come. The hardware has caught up to the demands of machine learning algorithms. We have better algorithms today, and we understand a little bit better how to effectively use them. So it's playing a role in many of the applications, and I see it as really a valuable tool for us to solve our problems. It's not going to be the thing that solves the problem. It's going to be the thing that helps us in getting to a solution.
And then Jim at Nokia Bell Labs asked, what advances in software need to be undertaken to make fuller use of machines like Frontier? What is Frontier, Jim?
Frontier is the fastest supercomputer.
Okay.
It's the thing which has some millions of cores in it, and is a hybrid system using both commodity processors and accelerators. And today we have a struggle in using that computer because of the software ecosystem. So today I have to write a program that uses the CPUs, and then I have to write another program that utilizes the GPUs. And we have to hand off data between the CPUs and GPUs to effectively use that architecture. So we need to come up with a better way of doing that. That distinction between the CPU and GPU is going to fade as we go forward. Those boundaries will collapse so that we'll just have one device, which is the CPU GPU, as an integrated system. But the programming of that is something which is going to be important to develop. We need to develop better technologies to effectively do that. We need to have a way of modularizing the application so that we could easily fit those modules in and change them as we move from one architecture to another. Today, if we move from an NVIDIA-based system to an AMD-based system, there's a major change that has to take place in the applications. So we need to have a better way of doing it. There's no easy solution to this. We need to be able to have maybe domain-specific languages developed, application-specific languages developed to help us in terms of easier implementation of our applications and moving that would allow us to move things forward.
Interesting. So thank you, Dr. Dongarra, for your extremely insightful presentation. Can I get a virtual round of applause from the audience again?
Okay, thanks very much.
And then just to kind of wrap things up here. So Dr. Dongarra, I'll be following up with you shortly to inquire where we can send you Godiva chocolates as a speaker gift for your willingness to take the time. We just want to extend our deep appreciation to coming to speak with Georgia Tech. Thanks as well to everyone in the audience for your attendance, and we'll see everyone here next week. We're going to have Edward Feigelbaum present.
Okay, thanks so much for your help. All right, take care.
Thank you.
I know.
Bye, everyone.